All right, hopefully we're back. So these are the force and moment models for the small perturbation. So we're saying that FAX, the aerodynamic X force, is the derivative of the full force evaluated at steady state times the perturbation. So again, we slope up away from the steady state flight condition, multiply by the variable. So you can just think of it as y equals mx, where x is the small perturbation. Alpha, same deal. Here's our alpha dot perturbation. Here's the Q perturbation. There's elevator and flap. So we're going to derive expressions for each of these derivatives so that we can fill in a matrix or a table that tells us how to calculate the small perturbation forces and moments. So the first one that we want to do is the U derivative. We have to do some preliminaries here to describe the forces and the moments, because in steady state, we're in the stability axis, of course, because that's where we're doing our analysis of. So there's XS and ZS. And here's our body fixed axis, X and Z. And this is alpha 1. So I'm drawing this just for context. So the steady state forces and moments are in the XS, ZS axis system. But now we have a small perturbation, alpha, on top of that. So our relative local wind at this instant in time with the perturbation is coming in from this direction. So what that means is that lift and drag are tilted slightly by that angle alpha, which is really annoying because that means we have to include components of CL and CD to get a force in the X direction. Because these FAXs, FAZs are in the XS, ZS axis system. And remember, we're evaluating them in that stability axis, steady state flight condition, but we have to account for these perturbations that happen. So that complicates things a bit, but it's important. People have discovered that it's important to include this. So what this means is that FAX in the stability axis in the stability axis system, so you might put an S there, is, sorry, this is total. Yeah, in the stability axis is going to be CD in the negative direction because it's pointing backward. This is CD this way. But we have to include CD cosine alpha to get it in this XS axis system. And then we're going to have a little component of the lift acting forward, this component here. And so that makes this more complicated than you would think it would be. You would think lift was in the Y direction or Z direction and drag is in the X direction, which is the whole reason we chose stability axis system for steady state. But because now we're perturbed through this angle alpha, we have to include both components, and we have to put Q bar S here to get the total force. The same story goes for the Z direction. is we're going to have mostly lift when alpha is small. But we get a little component of the drag as well, because this drag vector over here has a small vertical component in the stability axis system. There's no way around this because we have to get the components of all the forces in the correct directions. And so if it seems confusing, just think, well, our axis system is XS and ZS. So we have to get the forces in those axis systems. The perturbation shifts the lift and the drag directions because they're defined as perpendicular and parallel to the relative wind, and so that's what creates the complication. In the lateral directional direction, we don't have to worry about this because alpha is in the longitudinal forces and moments. And of course, the moment is easy because it doesn't matter whether we're shifting an alpha or not, the moment is still calculated around the y-axis. So this is just Cm Q bar S C bar. So for each of the variables, the first one we're going to look at is U over U1. So this is a small velocity perturbation. And we're going to look and see, well, what does that change? In these formulas here. So I'm going to have to scroll up past these. So make sure you have these written down because I'm going to take derivatives of each of the parts. We're going to have a derivative of CD. We have a derivative of CL. And we want to make some approximations on these before we get into the derivatives. So we're going to say in this formula above that alpha is small. And so can we help ourselves out a little bit with the complexity here? And we can say the cosine of a small angle is approximately 1. And the sine is the angle in radians. Again, we don't want to say 0 because that knocks too much out. But for small perturbations, we can do this. And it's not like this knocks out this whole term here. It doesn't. So that's a valid approximation. So the derivative down here of f a x with respect to u over u1, remember we're going to evaluate at the steady state flight condition, is going to be q bar s. And then the stuff inside the bracket we've got to differentiate. And then we're going to have another part, which is the stuff inside the bracket. And then we have to take the derivative of the dynamic pressure. Because the forward speed changes the dynamic pressure. And let's see, I should have had a derivative in here. So we're doing the derivative of this product. The first product is this part here. Then the second product is this part here. So yeah, this is tedious. I told you that this is not, the next couple lectures are kind of tedious because we're just working through all of these terms. But when we're done, we'll have a matrix so we can calculate these small perturbation forces and moments. The one thing we need to look at is this change in variable, because we're taking the derivative with respect to u over u1. So really we're saying, well, we have some other variable, call it s. It's called u over u1. And so if we're going to take the derivative, we're going to take ds. It's the same thing as du over u1. Or if you want to, think of it as delta. Because the derivative is just the limit of small deltas, right? So what this says is that if we're going to do this derivative, we can take the derivative just with respect to u, and we multiply by u1. Because there's several different ways you can think about this. One way is to replace ds in that formula by du over u1, and then the u1 pops up into the top. So either way you want to think of this, you're going to have q bar s, and then u1 times the derivative with respect to u of that thing in the bracket plus the bracket u1 derivative of q bar with respect to u times s. So we're going to do this in two parts. I want to call this part 1, and then this part 2. And we're going to do part 2 first because it's harder. So we have to take the derivative of the dynamic pressure with respect to our small perturbation. And the dynamic pressure is ½ rho and the total magnitude of the velocity. Like I said, this is tedious and complicated, so track with me here if you can. Where is u? We're taking the derivative with respect to u. It's going to show up here, not here, and not here. So the derivative is going to be u1 times ½ rho times 2. The 2 comes from this part here. u1 plus little u, and then the derivative with respect to what's inside. So that's our derivative of q with respect to u1. And we look at this, and now we have ½ rho u1 u1 and we're going to say this is small. So ½ rho u1 u1 is u1 squared, so that's q bar at the steady state flight condition u1 multiplied by 2. It's a lot of work just to get that, but that's the part that needs to go in up here. And then the second part is easy because what's inside this bracket up here is and we're saying, well, what is the derivative of that with respect to u over u1? And we're going to say that this is a small number because it's got alpha in it, and the derivative with respect to u of CL or alpha is going to be small. So really, part 1, which I said was easy, is super easy because we're just going to call this CDU. When you see this, you look at the U here and you go, oh, that's just the derivative of CD with respect to U. That is not correct. You have to remember that this is the derivative with respect to this non-dimensional thing. You'll see that happen over and over again. It goes back to the fact that when people were writing books, it was really hard to typeset a CD subscript U / over U1. So when you see CDU, it is the derivative with respect to this thing here. All right, so this is a really long story, but we're getting to the end of this part. We are calculating this derivative, that is, how does this aerodynamic X force change with a small perturbation U over U1? And we did this part, and we just have to add them together. And it boils down to just this part here and this part here added together when we were all done. So at the end of all of this work, it's always nice when it turns out to be not so complicated, huh? So that's part one. And that's part two. And now we need to do something really important. I hope some of you have your book, and you can look at page 147. Does anybody have their book here? So, page 147. I'm going to have to switch back to my other computer here for a minute. So we're looking at this page, right? This is FAX over Q bar 1S. So what we've done is we've derived this first entry in this matrix, because that's the stuff that multiplies U over U1, right? That's what we just did, the derivative with respect to U over U1. CDU, that's what we got. And then what do you have for this term right here? Do you have a CD or a CL? CL? Notice I marked something out here. It's because in older editions, there's an L there. And in newer editions, there should be a D. Do you have a D? If you have an L there, it should not be an L. It should be a D. It's a typo. We'll derive these other formulas, but if you look at just pattern matching, here's CDU to CD1. Down here, we're going to do the Z direction, and that's CL, because L is in the lift direction, and this is CL, and then CM and CM. I think what he did was he cut and pasted from here. When we derive these, it's actually going to flip to CD and CL, CL and CD. I'll show you why that is. But make sure if you have this typo in your book, you fix it. Otherwise, you'll calculate the wrong numbers. And this is what we're doing, is we're filling in each of these parts into this table. And then some homework problems and exams, you'll be pulling up this matrix and multiplying by the small perturbation variables to calculate the forces and moments. So the next thing that we need to do is the derivative of the Z force with respect to U over U1. And it will turn out to be exactly parallel, except the roles of CL and CD are switched. In fact, in this one, we'll say this is small, and we keep the lift, so that's why we get a CL in both those terms. And we still have the Q bar, so the derivative there is the same as what we just did. So we're going to get a CLU, and then that same derivative with respect to Q bar in terms of U. So in fact, we don't even really need to derive this. We're just going to say we're smart enough that we can just look at that and know that if we needed to, we could do this. Really, everywhere you see a D, you just replace it with an L. Notice the minus sign here. And I might have lost my minus sign up here. Let's look. No, I didn't. So there's a minus here and a minus here, and so that's pulled out in what we did here below. And again, the reason for that is if you look at the Z force equation, you just have, instead of CD, you have CL, and so everything else is just parallel to that. And then pitching moment, this one's easy because you don't have the components of CL and CD. So we just get CMU, the derivative of CM with respect to U, and then the second part is the derivative of Q bar, just like we did before. So this exactly parallels this. You just replace L or D with M, because the force in the moment is just either CD, CL, or CM times Q bar S. No. The reason these had a negative sign, let's go back up to the formula. That's a good question. The reason those had a negative sign is because there was a negative sign here and here, but there is no negative sign here. And so now I'm going to say, well, why is there a negative sign here? Anybody answer that? For $10,000? This is Jeopardy. Yeah. The X, well, we're talking X. X is forward positive, but drag is backward, right? And you're talking about this one, Z is down, but lift is up. So that's why there's those negative signs. But pitching moment is just pitching moment defined in the positive direction. What is what? You have to shout. Okay. Yeah, sorry, this ventilation system and just mask and everything. We might as well be doing this in a cave. Now I'm going to ask another, not philosophical, but let's go back and make sure we're doing this, is why do CL, CD, and CM vary with forward velocity when CL is lift divided by dynamic pressure, which includes the velocity change. We actually said this last time or the time before. You remember why we said varying U changes CL, CD, and CM? We know it changes the dynamic pressure, and we included that part, but why do we have CMU, CLU, and CDU? The lift is non-dimensionalized by the dynamic pressure. What could change with a small, say a 0.1 knot variation in velocity forward? Do you remember what we said? If you don't, flip back in your notes. because we talked through this. It's important to remember this. It's a Mach number effect, right? If you're flying at Mach 0.83, right near the critical Mach number, small changes in velocity change the shock waves, which change the lift, drag, and pitching moment. So that's why these terms are included. Typically at low speeds, in fact, when you look up these numbers in the back of the book for like the 182 airplane, CDU and CLU and CMU will be 0 because they're flying at low speeds and the effective velocity changes are non-dimensionalized out of the derivatives of the coefficients. So let's look at our matrix again. What's next? We just did this column here. And it's nice that they put the equations where you can look up the formulas for these. All right, so here's the equation for this. Here's the equation for this. Here's the equation for this. And how you can calculate those. And those multiply U over U1. So next, we need to do alpha. That one's going to be easy because alpha doesn't show up in Q bar. So that's nice. U did, and that's because we have U1 plus U in the dynamic pressure, whereas alpha comes from just W, which is squared, and it's small, so we knock it out anyway. And then a harder one is going to be alpha dot. That's the lag in the downwash. And then this is the effect of a pitch rate. And again, we're talking about these are small perturbations on a steady state flight. And then the elevator one will be super easy because we just say it, essentially. Here's CD delta E, CL delta E, CM delta E. So we'll do this, and then I think we'll be out of time today, which is good because this is tedious, and this takes a little bit of time to figure out these. So to break things up, I think I'll switch to the board. If that's okay with everybody, just to do something different, keep everybody awake, including me. Is this cold weather making you sleepy? I woke up Monday morning. I was like, I didn't want to get out of bed. It was just cold. I'm assuming my microphone's still working, right? Good. I think it was, I did it, you know, sometimes using computers, I was thinking this today, back in ancient times in the Greeks, they had the gods of everything, the god of the plants and the harvest and all that. It's almost like praying to the god of the computer, and you have to do it in exactly the right manner in order to get it to do what you want to do. And what I did today was I launched Zoom and then I plugged the microphone in instead of plugging the microphone in and launching Zoom. Isn't that weird? So I guess now this suddenly turned into a philosophy class in ancient religions, huh? No, that's still flight dynamics. That was just to wake you up. So next is the alpha. Perturbation effect. This is a dimensionless parameter because it's W over U1. So it's nice already. We don't have to non-dimensionalize it. That also makes that derivative easier because I have to go through that whole explanation of why derivative with respect to U over U1 is U1 times the derivative with respect to U. That complicated things and got us distracted. All right, so we have these same formulas. And again, a reminder, where did these come from? It comes from the fact that when we're tilted down at that little angle of attack, perturbation, then we have components of CL and CD in different directions. And the U derivatives were complicated because we had to take the derivative of Q bar and this stuff over here. Now we don't. So this is a lot easier. So let's do the alpha derivative here. So we look at this and we go, drag changes with angle of attack, we know that. There it is. Now CL, so we got, does lift change with angle of attack? Well, sure, definitely. Does angle of attack change with angle of attack? That's the easiest derivative in the world, right? Does dynamic pressure change with angle of attack? The answer to that is, it depends. Where is alpha? Alpha is in here, so really we have alpha squared inside here. So does that change with angle of attack? Yes, but it's squared, and it's a small change squared, so we're going to say that that's small. So we can knock that out. Why did we not knock U out? We talked through this last time. It's because if you expand this thing out, you still get a big number here, even if you knock out the U here. So we have to include a derivative of that with respect to U, but W is all by itself out here. It's small compared to like U1 squared. All right, so that's one. We knocked that out. And now this takes a little bit of explanation because we know that this change is important. That's CL alpha times alpha. And here's CL. And then this is CD alpha. But the book's going to say, well, we can say this is small. But that's the little change in lift. Now that's not the full alpha, remember. This is a small perturbation alpha. So that's not the total lift, that's the little change in lift due to alpha. So you'd say, well, maybe we want to include that, but what are we going to multiply this by? We've got our derivative here in the term for FAX. We've got the U stuff, and then we're going to take that thing, and we're going to multiply it by alpha, right? Because we're taking the derivative of that with respect to alpha, and then we multiply it by the change in the x-axis to get the value. So we're going to end up with alpha times alpha if we keep that term. So that's alpha squared, so it's small. And it's going to be nonlinear, so we can't Laplace it, so it's doubly bad. So we don't like it, because it's going to be a problem, and it really is small. So we're going to say that this is small because it's going to be multiplied by a small variable, and you're going to get small times small. We could keep it, and then once we plug it in, we'll all see, oh yeah, it's small, and we'll knock it out. So let's knock it out now. So what we end up with in this is minus CD alpha plus CL. And remember, we evaluate this at our steady state flight condition, so we're just going to pick up whatever CL is in steady state, so that's CL1. So that's our lift coefficient at the equilibrium flight condition that we're taking our derivatives at. So that's what shows up in that matrix, in that entry. And if what I just said about taking the derivative of the steady state flight condition still is a little fuzzy, let me draw another picture to sell that story. So instead of talking about all these variables, let's just talk about f of x. Here's f of x, it goes like that. What's the slope? So I would say for 10 points extra credit, calculate the slope. What are you going to ask? What part, right? Where on the curve do I want the slope, right? So that's what we're really doing here. I'm going to say, well, here is x1, that's my steady state flight condition. And then I'm looking at a small perturbation, delta x. So I'm going to take my slope and calculate it at the steady state flight and then use that to project to that new position. Because that delta x is so small that that curvature doesn't really count so much. So that's what we're doing with each one of these, is we're writing a linear line equation for each of the variables separately, and then just adding up all the slopes. So we got a slope in the alpha dimension, we got a slope in the u dimension, we got a slope in the elevator dimension, and a bunch of other dimensions outside the space that we live in. All right, so the z derivation, you can see, same deal, we're just going to switch CL and CD. And notice in this case, we get a D here, but we get an L here, because the double terms didn't come from the very first term like they did in the U perturbation, because with that one, we got a term from here and a term from there, and we knocked that out completely. But here, we got a term from the first one and a term from the second one, and so that's why we get D and L. So the derivative with respect to FAZ comes straight from here, and we just flip D and L and make sure we get the signs right, and we're good there. So that's the CL derivative of the first one, and then the second term gives us a CD1. And so that's the formula for that. In the pitching moment, is so easy because there is no component L and D. We just take the derivative of this with respect to alpha, which gives us CM alpha, and we all know what that is already. So now we have the second column in that matrix. Now, along the way, we're talking about small perturbations, and we knock terms out whenever we get essentially second order terms like alpha squared or u times alpha, stuff like that. You don't have to do that. You can be more accurate by including the second order terms in these polynomials. Just like if you're trying to curve fit that f of x function, we're saying we're curve fitting it with a line, but if you added a second derivative, you'd get the x squared term, and so you could fit it a little better, right? But the reason we don't do that in our small perturbation analysis is we want to take the Laplace transform to do, because it's dynamics equation, so we're going to solve it with Laplace transforms, and you can't take the Laplace transform of alpha squared. It's just not defined. It doesn't do nonlinear terms. Okay, I promised you we'd stop here, so we're going to. The next is the alpha dot effect, and we'll start that next time. You guys have homework due next time, right? Anybody have questions about that? I've helped a couple people in my office. If you get stuck on the code, come see me. I'll try to help you. Yeah. IH, yeah.
So you said hard copy. You need hard copy.
That's left over from the days the days meaning last year before COVID. I just want you to scan your hard copy. Make sure you write it out, scan, and then just upload it. Yeah. You're not turning in hard copy in class because that's just my policy for this semester. Did I tell you about quiz number 1 in AE714? That I microwaved it? Yeah, I microwaved it to kill the germs, which turns out doesn't work, and almost caught them on fire. Any other questions on the homework? I answered your question down there, right? Yeah, okay. Anybody on Zoom have a question? You guys can talk, you know.
I was curious, the next exam is the syllabus says it's Thursday. Is that still what you were thinking?
I'm going to be looking at that. I knew it was coming up, so let me see about the timing.
Up to longitudinal perturbation forces and minus.
Yeah, so we need to get through these. So the timing, we should be through these next time. So it'll either be that Thursday or the next week after that.
Okay.
Let me see where we are in homework. I'm going to look at the next homework set, and then I'll set the date for the exam. But it won't be any earlier than next Thursday, but it might be next Thursday or it might be the following Tuesday. Okay.